Hello, everyone. Thank you for being here. Today we have hello. Today we have Yann Barabinot to present part of his work. He's from the physical oceanography group, and I hope you remember well the presentation from Diego because it will be the same topic. So
Thank you. Thank you. So hello everyone. In this presentation, I will talk about what I did during my PhD, and in the second part, what I did here. So I did a master in fluid dynamics, and for me, it was always natural to start from fluid dynamics to go to the ocean. So this is the point of view I chose for this presentation, and I hope you will like it. So we start here talking about the coherence in fluid dynamics. So our story starts in the 15th century with the work did by Leonardo da Vinci. He is one of the first men who described what was turbulent flow, and he used a keyword here, eddies. And so we will talk about this also in this presentation. So you have also beautiful drawings from Leonardo da Vinci, of course, and he described turbulence as a set of disconnected eddies plus disorder. 4 centuries later, we have the century of theory, which is the 19th century with big names in fluid dynamics, so Navier, Stokes, Kelvin, Poiseuille, Helmholtz, Hagen, among others. They worked on the framework that is still used today to describe fluid dynamics and fluid flows. So they work on continuity equation or conservation of mass, Navier-Stokes equation, which are famous because this is part of millennium price problem. So if you have time to waste, you can try to find a solution. And we have the introduction of concepts like vorticity or viscosity to describe flows. But it was only a theoretical studies on fluids, so the theoretical framework, and there is no study of turbulence as such. This century concludes with the Reynolds experiment, which is well known in fluid dynamics because this is the first man who has studied the transition between what we call laminar flow and turbulent flow in pipe. So here is a drawing of the experiment. So he was studying the movement of fluid in a pipe, and he observed that if we increase the energy or if we increase the flow rate, we can observe the transition to turbulence and to this disorder when this number reached critical value, and this experiment is well known. So, and he also observed that turbulence was able to mix colored and uncolored water. So at this time, turbulence is just a set of edges, disorder, and mixing. Or at least this is what we knew at this time. And in the early 2000s, in the early 20s, we have a paradigm shift due to the improvement of experimental techniques to observe flows, such as the use of smokes, lights, or floating particles. And we observe that in turbulence, we have large organized structures. And here I'm showing 2 examples. So the first one is here, a gaseous jet from Brown et al. In 1935, where you can find large structures, large eddies of smokes. And here is another classical example. So this is the turbulent boundary layer. So a flat plate with a turbulent flow. The arrow indicates the direction of the flow. So here, this is turbulent, so disorder, you can't see anything. But if you look at the flat plate from the side, you are able to see like small bumps, small loops of smokes. And those loops are in fact vortex tubes, and they remain quite stationary. And we call this kind of vortices hairpin or horseshoe vortices. And so it completely changed the way we saw turbulence at this time, because turbulence is just not only disorder, but also we have organized structures in it. But the word coherence has not been introduced yet. After that, in the early 80s, we have a first definition. And just for fun, I found what coherence means in the 16th century and in the 19th century. So in the 16th century, it meant harmonious, logically linked. Okay, and in the 19th, it means mass or materials that adhere or clings firmly to a whole, held together by a cohesive force. So it had a bit of sense to call those structures coherent. But the first physical definition came from the work of Hussein and collaborators with the two big articles in 1983 and 1986. And for them, a coherent structure is the mass of non-viscous turbulent fluid with a large-scale vorticity component that instantaneously dominates the three-dimensional vorticity of the turbulence. Okay, so this is just big eddies. And they provide also a statistical tool to separate coherent from incoherent parts in flow. And maybe some of you know the proper orthogonal decomposition because this is still used today. And it comes from their article. But okay, this is complex and qualitative definition, and those statistical tools are not easy to apply because we have to obtain a temporal series, and so it's not, I would say, easy to apply. And so for some researchers, coherence is just large-scale structures with their own spatial territories, and coherent is what we see. And even Hussein wrote in his article that in principle, it's preferable to leave concepts such as coherent as implicit because they are very difficult to define. And also just for fun, I tried with the corpus of Google Books to recover so the occurrence of coherent structures in turbulence. And you can see that you have a big pipes around the 80s. So this is the time where people started to use this expression. Okay, so now in the 80s, still in the 80s, we have the first application to oceanic eddies due to the work of Mark Williams, also in two big articles in 1984 and 1986. And it was at the time where numerical simulations have had much power, start to increase in terms of power. And so we were able to compute and to simulate oceanic turbulence, which is called geostrophic turbulence. And here, this is an example of one of those simulations. So here, this is the logarithm of the relative vorticity. And we can observe large eddies, large loops of currents in this simulation. And so those eddies have their own territories. They are by definition a dominant vorticity component, a non-viscous fluid. So they are coherent in terms of, according to Hussein's definition. But for Matt Williams, in his article, coherent just means which lives a long time. And as he applied this definition to oceanic eddies, this is still the vision we have of a coherent vortex in the ocean. And we will call this definition the kinematic coherence as a sufficiently persistent rotational flow created by turbulence. And we classically use Eulerian criteria to describe them. I will come back to this later. In the ocean, eddies look like that. So this is a view from satellite data of the Gulf Stream. So you can see that the Gulf Stream is not only a current, but you have also many mesoscale eddies in many loops of currents in this Gulf Stream. They have a typical size of 100 kilometers, and the classical orders of magnitude for the flow is 1 meter per second, but it can vary depending on forcing and the region. So yeah, the key point is here that eddies matter in the general circulation in the ocean, and they are known to play an important role on the large scale circulation, and they are as important as the large scale circulation. They also help regulating the climate because they are able to trap the water mass and transport heat and and biogeochemical traces from one region to the other. And so, yeah, they are important. And after with this idea of transport, we have the apparition in the early 2000s of Lagrangian framework to understand fluid particle trajectories to quantify mixing. And one of these framework is the Lagrangian coherent structures, so LCS. I will not go into the detail of this framework because this is a bit complicated, but this is just to study trajectories of fluid parcels. So here, for instance, are examples of trajectories, and they classify sets of closed trajectories as elliptic LCS. And so they decided to say that some eddies could be elliptical CS, so closed trajectories. And we ended with a second definition of coherence, which we will call the material coherence. So it was first proposed by Barabinot and Euler in their paper. And for them, an eddy remains coherent as long as it has not lost the water it trapped during its formation. And so we classically use Lagrangian criteria to describe this coherence. So just a quick recap from Diego's presentation. In fluid dynamics, we have classically two visions, two ways to analyze flow, depending on the tool we use and what we want to prove. But we have also the Eulerian view of fluid dynamics, which is just we remain fixed and we analyze the field from this fixed point of view. And in the Lagrangian view, you try to analyze fluid trajectory, so you follow the fluid parcels, yeah. And so if you want to know more, please talk to Diego. He's the expert. So what is the consequence of those visions on transport? Because this is what matters in the ocean, the transport of heat and salt from one region to the other. So here I'm choosing an example from Barabinot et al. In 2013. So they detected an eddy here in the South Atlantic Ocean. This is the geostrophic velocity from SSH, conventional altimetry for the experts. And they applied Eulerian criteria to characterize the core and Lagrangian criteria to characterize the form. So in red, this is the same eddy, but in November 2006. And in yellow, this is the same eddy, but 4 months later, in February 2007. And they performed particle tracking, so they observed the movement of particles from those 2 days, between those 2 dates, depending on whether we use Eulerian criteria or Lagrangian criteria. And you can see that if we use Eulerian criteria, parcels are able to escape the core, and we have some leakage, whereas if you use Lagrangian criteria, particles remain trapped in the core. And so the expert would say that the Eulerian criteria serve to really quantify the transport. And so actually the scientific community is divided between those two visions, because from one side, according to Lagrangian defenders, the number of coherent eddies is low, but according to the other side, the number of coherent eddies is huge, and thus, from one part, the transport by coherent eddies is negligible, whereas it is huge in the other point of view. And so, one of the this is in this context that I started my PhD, and one of the questions we had is how to conciliate both vision, especially when using in situ data. So, to study the structure of oceanic eddies, we need to go at sea with a boat and to perform a succession of vertical profiles in the ocean to measure properties such as temperature or salinity on the entire water column. So for instance, you try to target an eddy with the boat and you try to cross it in the core, and so to create a 2D vertical cross section. And so interestingly, this vision is as if you try to take a photo of the flow. So this is a Eulerian view of the flow. And here is an example of such section. So for instance, here we are in the South Atlantic Ocean, close to South Africa. So this is the depth in meters. This is the horizontal scale in kilometers. And I'm plotting the velocity, for instance, of the flow. So you can see that it can reach 1 meter per second or more. And for the experts in the room, we can see that we have one anticyclone, so one cyclone, one anticyclone, and one anticyclone here. I will not describe how we are able to detect them, but yeah, just to show you that what an example of cross-section. And so, as I said, Lagrangian criteria cannot be applied on in situ data because they are interestingly Eulerian, and you don't have any information about flow trajectories. And so we wanted to find another proxy to detect whether or not an eddy is able to transport a different water mass from the environment. And so we defined what we call the thermoline coherence. And we started with a thought experiment. So let us take one part of the ocean, part A, with the temperature and salinity field, T0 and S0. And we consider a second part of the ocean, part B, with different temperature and salinity. Imagine we have a materially coherent vortex that formed in part A, and this is perfect. There is no dissipation, no diffusion, everything is perfect. And this eddy drifts towards the part B. Ooh. And after, we observe that you have water with different properties that is coming from part A to part B. And so we are able to detect the anomaly, so this difference of temperature and salinity in part B. And those anomalies can be computable, can be computed with in situ data. And so we define the thermal coherence as an eddy transporting a different water mass from the surrounding water, which is a direct consequence of the material coherence. And so here is an example. So for people who love math, we compute thermal anomalies on isopinal surfaces. So I will not go into the detail of that. But here is an example of the core of an anticyclonic eddy sampled in the North Brazil current region. So as before, this is a depth estimator. This is the horizontal scale in kilometers. And you can see that the core is associated with a large negative anomalies of both temperature and salinity, showing that the water trapped in the core is indeed different from the surrounding water. And to prove that this methodology actually works, we can retrieve the origin of the water mass. We can associate water mass with those anomalies, because in the ocean, water masses are associated to regions, and temperature and salinity is like the signature of water masses in the ocean. And so here, this is what we did. And so, for instance, the upper part of the core is associated with this orange patch here, and with a bit of research, we can retrieve that the water here trapped comes from the South Atlantic Ocean, so the region close to South Africa. But remember that we are in the North Brazil current region. So that doesn't mean that the eddy has been formed there, but at least that here the water mass associated to the anomaly is indeed different from the surrounding water. And so it proves that you have a transport. What can we do with that? An important result was the location of the core, of the coherent core on the vertical. So for instance, this is the previous 2D cross section. And so this is salinity anomaly. And you can see that pretty much all anticyclones are associated with a clear anomalies on salinity. And those eddies are in fact detected by satellites. And this is my key message. So even if the eddy is detected by satellites, most of the time the core is located much below, so around here, 150 meters depth. And that was the case for 60% of the eddies we had. So my key message here is that surface products are not sufficient to assess the material coherence of eddies. So we need to have information of the entire water column. So the conclusion of this first part is that the thermal coherence is a Eulerian proof of a Lagrangian transport, and the coherent core is often localized at depth. So yeah, you cannot use only altimetry and surface products to quantify the material coherence of eddies. So now I wanted to say a few words about what I did here at IMEDEA. So we will talk about turbulence, energy cascade, and altimetry. So if we come back to fluid dynamics, here this is also a gaseous jet with smokes, and you can see structures in it. You are able to observe coherent structures, but those coherent structures are immediately destroyed towards smaller scales and to create smaller scales. And so this is a key properties of classical three-dimensional turbulence. Structures break to create smaller ones. And so the energy cascades towards smaller scales. And so in the ocean, the first step of this cascade is our mesoscale eddies. It's the first step of turbulent cascade. But in the ocean, the dynamics is almost 2D. I will not go into the detail, but it's almost 2D, and mesoscale eddies do not break immediately. It takes months. And so we have what we call intermittency. So the ocean creates structures of different size that coexist. And so here is a beautiful view of Eulerian in 2021 from the Gulf Stream. So this is still the relative vorticity. And you can see a huge amount of structures. So you have large mesoscale eddies here, of course. You have the main Gulf Stream, and you have a soup of, we don't know, a lot of things. But if we come back to our cascade of energy, so you are able to see what we call the mesoscale, so the first step of the turbulence cascade, but also what we call the sub-mesoscale, so this soup of undetermined structures. You can see filaments, smaller eddies, and everything is coexist. So in terms of, so we can, to study those structures from the sea surface, we can use altimetry, so satellites data. And before, we had what we call the conventional altimetry. So those are the products with a resolution of a quarter of degree, which is almost 25 kilometers. And if you remember the size of an eddy, this is 100, approximately, depending on the latitude, but 100. So you had only 4 points in average to sample an eddy with a satellite data. Whereas now we have SWOT satellite, which is much more precise, and it is able to sample the sea surface with a better precision, I would say. And so before we were only able to detect mesoscale, but now we are able to detect mesoscale plus a part of the submesoscale. And what is important is the energy, of course, and to quantify the energy of the turbulence in the ocean, we often compute what we call the eddy kinetic energy. I think this is pretty clear, eddy kinetic energy. And so in one case, we have only the mesoscale. So we expect an eddy kinetic energy smaller than if we consider the SWOT measurements, because we have mesoscale and submesoscale. And as I said, because all structures coexist, if you don't account for submesoscale, your energy is underestimated. And this is what we obtain. So here is the average mean eddy kinetic energy over a 3-year period from August 2023 to August 2025. So A is from SWOT, the new satellite, and B is from the classical conventional altimetry. And so as you can see, the energy is much higher in some case. This is the same polar bar. So you can see this is almost negligible compared to what we are able to measure with the submesoscale. And if we plot the time series, this is what we obtain. So in pink, this is classical altimetry, and in green, this is SWOT data. And so here, the key points are that the eddy kinetic energy is 1.8 times higher, serving the submesoscale. You also observe a clear seasonal cycle. So the EKI is low in winter, in summer, increases in winter, and so on. And the EKI, it increases by 50% in winter with respect to summertime. To finish, here are snapshots. So this is the map for the EKI in minimum, so in summer. And this is the map for the EKI maximum in winter. And as you can observe, you have much more yellow structures in winter. So I end my presentation on this. Thank you very much. And I hope you found my presentation coherent. Thank you. Questions? Yeah.
Yes, so very nice topic. I understand very well because you explained very well the notion of coherence, but I was having questions about what we call probably what like this in your community, the disorder coherence.
I think those are just attempts to describe what we cannot explain. So I don't know if disorder before has the same meaning as disorder now, because you are referring to chaos theory and so on, no?
Yeah, on one part, on the other part, there is the thermodynamic definition of disorder.
Yeah. I think for me, disorder was just a matter to say that, okay, we saw turbulent flow, we don't really understand what happened. You have particles, fluid parcels going up, down, left, right. So we don't understand. So this is disorder. This is the way I see it. But this is I don't think in the 15th century it has a real physical meaning.
Nowadays,
I don't know. I think the definition of what is a turbulent flow is open. There is no clear definition of what is turbulent, and there is no model to really explain how why a fluid is changing its behavior when you increase the kinetic energy in terms of molecular scale. Why this behavior? I think this is still an open question.
What you're going to explore your new postdoc in the
No, no. In my new postdoc, I will change the scale. So if we come back to this, in my new postdoc, so PhD mesoscale, for the first postdoc sub-mesoscale, and the second postdoc, this is not viscous scale because viscous scale is the scale at which the viscosity starts to act, but there is a scale in between that we call mixing in the ocean. And so, yeah, I will study this mixing length. Yeah.
What is the process that transport the energy from mesoscale to submesoscale, and also from submesoscale to smaller scale, as you said, you discussed range?
Yeah. So in classical fluid dynamics, instabilities, so you have large structures, they are unstable, they break. So the energy it creates in the ocean, you have one eddy, it breaks two eddies. So you have a transfer to a smaller scale. And after, I think this is the same in classical fluid dynamics. Actually, barotropic instability is just the adaptation of Kelvin-Helmholtz instability in a way in classical fluid dynamics. But this is just to say, because the ocean is stratified, so you use the term barotropic, but for me, the physics is almost the same.
And another question, is it possible that the energy transfer inversely?
Yeah, because this is in average. But in the ocean, you observe merging also of mesoscale eddies. So at some point, you have two smaller structures that merge to create a bigger one, and it occurs. But I think I don't know, the classical behavior is in average this one. But in the ocean, it's complicated because you have several length scales, time scales, whereas just if you study a jet, you have only the length scale is just the so here the length scale is just, for instance, the diameter of the opening here. The time scale, I don't know, is just the flow rate as a function of the flow rate and the opening. So you have only one time scale, characteristic time scale, one length scale. Whereas in the ocean, you have several length scale, time scales. I don't know if and this is the problem of intermittency for me. The way, because several structures can coexist, that is the reason why ocean is so complicated to study. Yeah.
Very nice talk. I have two very good questions. Did you explore another techniques like Google waste parameter? So the first one, And in the second one, you're analyzing here the direct or more of cascade, no?
Yeah. Yeah.
Big to small scale.
Yeah.
Do you have any clue about the inverse transfer of energy from the small to the big scale?
Yeah, this is what I meant by merging of eddies. This is part of the inverse cascade, of course. But yeah, I don't know what you mean by clue, but but yeah, it occurs. Yeah, yeah, yeah. So yeah, what we observed is that depending on the length scale, you have if you take, for instance, larger scale above, I don't know, I remember, but classically this is around 30 or 50 kilometers. Most of the energy go upscale, but if you consider a smaller scale than 30 or 50 kilometers, most of the energy go downscale. Yeah, and so yeah, but here that was just a way to do a parallel between what we know in fluid dynamics and the ocean, and to explain really how and why the ocean is so complicated to study. Yeah, and for I don't remember your focus.
Okubo waves.
Huh?
Okubo waves.
Okubo waves. This is Eulerian.
Yeah.
Yeah, this is Eulerian, and you are still a leakage if you use it, and you are. This is part of what I call the kinematic coherence for me, and as it does not take into account trajectories, you cannot really assess transport with it. But this is common, and this is, I think, a good step to really detect eddies, but not really to assess a transport. But I know that some people are trying to create a Lagrangian version of Okubo waves. I don't know if it works. Yeah. Yeah.
It's not a quick question because in my book they are very interested in plantons. Do you know a bit about people looking at transport also mixing with the question of plantons?
Yeah, sure. You have a lot of work because I saw, for instance, that some the eddies is creating also vertical velocities, and so vertical velocities are able to transport plantons at depth or inversely at the surface. So for the oxygen, so you are mixing, and so I know that it increases the NPP, the primary production. I'm not an expert, but yeah. And after, what is interesting is that I saw some articles showing that, for instance, some sharks are targeting some hot anticyclonic eddies because probably there are more fishes in it, and fishes are following plankton and so on. So I think yeah.
So after the fluid dynamic cascades, there's an ecological cascade.
Yeah, yeah. But I have a nice paper from Marina Levy, a researcher in Paris, and she published, I think, a very nice paper in Nature, and the title is, I don't know, no, Submesoscale from Physics to Life, and this is exactly that. Yeah.
Because I mean, it's super interesting this part, I think, because also it means that these eddies, they can transport also the nutrients from productive places to uneconomic places.
Yeah, sure. Yeah.
In this area that you studied, or they took also like biological or chemical samples?
I know that for this one, I have data from oxygen, for oxygen, but after.
I mean, because that one crossed all the southern Atlantic Ocean. Right?
Yeah.
Super interesting.
Yeah.
You tracked this one? Like you are sure that it will.
No, because as I said, you are not sure that this eddy has been formed in the South Atlantic Ocean, but at least that the water there has as going up northward, and that maybe the retroflexion of the north-boundary current has trapped it to transport it northward. But this one doesn't have a surface signature. So, and if you try to look at trajectories of this kind of eddies, or at least surface one in this region, they only they are generated only here, not there. So they start here and after they move northward. So I don't know. But yeah, I think it's pretty cool to see that the South Atlantic water is going towards the Caribbean Sea. Yeah.
My very last question. I really like the way that you describing from the history to the modern oceanography. And one of the slides you mentioned that you need to fulfill one criteria or value in order to have turbulence. So this theory of fluid dynamics also apply to your measure scale turbulence?
Yeah, but not in the way because you are talking about what we call the Reynolds number. So this part, right? So this number is also applied in model, but nowadays it is more used to separate scale at which viscosity play a role from scales in which the viscosity doesn't play a role. This is just because, for instance, in oceanographic model, you don't have viscosity. You have numerical viscosity, you have diffusion parameter, but you don't have momentum viscosity because this is too big, and viscosity starts to act. I don't know. If you put some honey in a table, you will see. I don't know what, a centimeter.
Yeah, which means in the larger scale, not will be this one. This parameter will not be useful.
I think it depends on the way you are defining it, because this is velocity times a distance dividing by viscosity. So the velocity you have it, this is a mesoscale or whatever, but the classical length scale, this is always the same problem. It depends on what you are looking at. So I think it can be useful, and maybe in some numerical models, they have it. But I think in classical circulation model, maybe Baptiste, I don't know if you have some. But I think this is too small scale to use viscosity. Yeah.
One question about your figure you showed about so you have done a search on
Yeah.
for
This one. This is you just need to type Google Books Ngram Viewer, and you can Google Books Ngram Viewer, and you can search for every expression you want. So cats, dogs, and it will, and you select a corpus. So here I'm selecting the English corpus. So I think this is all the database from Google.
So it includes published papers in general.
Yeah, all everything.
But you can select more like for papers or.
I'm not sure. I think this is general. But in the life, you don't apply coherent structures in turbulence. So
That we can do it so quickly, so we can do it with magnetic waves or.
Yeah, sure. Yeah, sure. But you can choose here. This is English. You can choose American English, and I think there are other options, but I don't remember. Google Books Ngram Viewer.
Yeah, this is right. How did you find it?
on YouTube.
What did you do?
Yeah, so I was watching a video and the guy was presenting this kind of plots, but that was just for his introduction, so I took the idea.
It's Google, it's not Google, it's a private
No,
website.
this is Google.
Google.
Yeah, this is Google. Thank you.
So we can leave it here. Thank you very much.